Okay, so what a Lewis structure does is represents the structure of a compound. So we, in essence, just did this with cyanide. There's a catch. With a Lewis structure, what we typically do, and I will copy this to here, what we typically do is once we've got all the bonded pairs in, we replace any of those 2 dots with a straight line. So that single dash represents 2 shared electrons. So we would replace this with what? Oops. What would we need? 3. We would replace that with 3 lines because that's 3 bonds. We have 3 shared pairs of electrons. Now notice that I didn't replace those last 2 dots. Why not? They're not shared. That's called an unshared pair. So we would show the structure for the cyanide molecule like that. We could show this, our little double bonded carbon compound. I'm going to get rid of all my funny circles. We would need to have 2 lines in there. These would each be a single line. And we'll talk more later about the direction that the things point in. That's a Lewis structure. Now on Lewis structures, this is important, we do leave these unshared pairs. If you draw something that you are claiming it's a Lewis structure and you don't show your unshared pairs, it's not a Lewis structure. Instead, it's a structural formula. If you go on to take organic chemistry, you will do tons of structural formulas. You'll get better at drawing pentagons and hexagons than you ever thought possible because a lot of organic molecules are what we call ring molecules. Let's do one with, well, let's do this compound. We haven't gotten to naming yet. I'll tell you that that's called carbon tetrafluoride. Nasty, nasty, toxic, poisonous stuff. Don't touch it. Don't play with it. But it's fun to draw. So to start drawing this Lewis structure, this is where we will go to the Gooch math. Okay, so the first thing we need to know for the Gooch math is how many of each type of atoms we've got. How many carbons do we have? 1. How many fluorines do we have? 4. And we're going to count up how many valence electrons each of these come with. So how many valence, I'm going to write this as valence E, val E. So how many valence electrons does carbon have? 4. How many valence electrons does fluorine have? 7. So we have 4 and 28. Total number of valence electrons? 32. Okay, so these atoms come in bearing a total of 32 valence electrons. Now, here's the question. If everybody was satisfied according to octet, if everybody met their octet requirements, how many valence electrons would the whole thing be? Well, how many does carbon want to feel like it has? Octet 8. How many does fluorine want to feel like it has? 8. It seems silly to ask when we're talking about octet, but remember that there are some things that are satisfied with less than 8. So we get here 8 and 32. Total number of electrons required for octet to be satisfied? 40. So now the question is, how many bonds is this going to form? Well, what is a bond? It's 2 shared electrons, right? So the number needed minus the number you actually come in with equals the number of electrons you're going to share. So 40 minus 32, these need to share 8 electrons. That makes sense. Well, what is a bond? It's 2 shared electrons. So the number of shared electrons divided by 2, shared divided by 2 equals number of bonds. So 8 divided by 2 equals 4 single, well, it equals 4 bonds. Now, something that you don't know yet, I'm about to tell you, is that whenever you do a Lewis structure, the least electronegative element or carbon goes in the middle. So if you've got carbon, carbon's in the middle, period. If you have no carbon, whatever is least electronegative, least attractive to atoms is going to go in the center. In the center, excuse me. We'll get into some other shortcuts in terms of how to tell what's in the middle. But in general, least electronegative or carbon, or if you've got 4 of one thing and 1 of something else, the singleton goes in the middle. So we're going to put carbon in the middle, and we know that we have 4 bonds and we have 4 fluorines. That's pretty cool. And how many valence electrons did each fluorine come in with? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. How many did they come in with? Why are you counting to 6 moles? Or they came in with 7, right? Where's the other one they came in with? It's being shared right there with 1 from carbon. I've just replaced those with a single line. That's the Lewis structure for carbon tetrafluoride. Now, we can check our math to see how many unshared electrons there are, because the beauty of the Gooch method is that it's all mathematical. So we know that these are, well, that these came in with 32 valence electrons. How many are they sharing? 8. Well, what does that give us? 32 minus 8? 24. So we have 24 that are not shared. Well, let's see. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 unshared. It's all mathematical for these, which is a real thing of beauty. Okay, sort of the old style of doing this, the way that I was taught, that never made much sense to me, but I'll show you just for sort of contrast. We start with our elements that are present, 1 carbon, 4 fluorines. I draw an electron dot diagram for each of them, and then I'm going to fit these together. So I can move this over here, and those two can share, and then I can move this over here. Well, I have to move one of these over here, and then I can put this fluorine there, and then I can move one of those over there, and then that one can share, and then I have to move one of these electrons to there, and then those can share, And then any place I have a shared pair, I replace it with a line. And it works okay on something simple like this. You can see how it all fits together. You can see where the lines are going to go. When we get into the more complicated ones, doing it sort of, I don't know, by guess and by God, yeah, this looks like it'll fit here, yeah, this will fit here, gets a little weirder when we get into multiple bonds. So hence why the Gooch math is a wonderful thing. The Gooch math nearly saved my sanity many years ago. This is where your book introduces this, and I think at some point I need to go in and reconfigure my notes because I don't know that it's the best flow here. We said that there are double bonds, and I showed you a double bonded carbon compound, and I know I'm using the fat lines, but that's okay. So there's no other place that double bond could exist, is there? Is there any place else that double bond could exist? How many times can hydrogen bond? Once. Carbon's the only thing in that compound that can share more than one pair of electrons. But there are substances where that's not the case. So I give you, well, we could do ozone, sure. So we have O3. Let's do the Gooch math for this. O3 is ozone. There's a big layer of it in the upper atmosphere, protects us from UV radiation. Up in the atmosphere, it's a great thing. Down here at ground level, ozone's a very bad thing. It produces smog, it kills plants. It's generated by running electric motors, actually, because you get some ionization happening, and you create oxygen ions, and you end up with ozone. Bad thing. Ground level ozone, not good. Upper atmosphere ozone, awesome. If only we could ship it up. Let's do the Gooch math. So, following the Gooch math formula, what's the first thing we want to calculate? Total number of valence electrons that this is coming in with. So we have oxygen, however many valence electrons that is, times 3. How many valence electrons does oxygen have? You have your periodic table out? 6. So this is coming in with 18 valence electrons. What would everybody require to be satisfied? So oxygen wants 8 times 3 gives us 24 octet electrons if everyone was satisfied. Octet minus valence equals the number of shared electrons. So 24 minus 18, how many electrons are being shared? 6. Shared divided by 2 gives you the number of bonds. 3 bonds. Okay, well with carbon tetrafluoride it was easy because we had 4 bonds and we had one thing in the center and 4 things hooked to it, and that was really simple. But here we're saying we have 3 bonds, and let's do that last step of how many unshared electrons will we have. So let's see. Valence minus shared will show us how many total unshared electrons we've got. Well, we had 18 valence minus 6 shared. So we're going to have 12 unshared. Okay. Set that over there. So if we have 3 bonds, I mean, here's the thing. We only have 3 things. So we can put a single bond there and a single bond there, but that's not the number of bonds we have. What has to happen? Somebody's got to double up. There's a double bond there somewhere. The nice thing about the Gooch math is you're never in doubt about whether or not there's a double bond. If you have more bonds required than places to put a bond, you have a multiple bond. So we know that there has to be a double bond. Well, let's put in our unshareds. So we have 12 unshareds. This oxygen on the end, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 2, 4, 6, 8, 2, 4, 6, 8. Okay. And that gives us for unshareds 2, 4, 6, 8, 10, 12. We have the right number of unshareds. How did I know where to put 2 unshared pairs and 1 unshared pair and 3 unshared pairs? I'm counting to 8 for each of those oxygen atoms. We're going to spend lots of time practicing these, don't worry. I'm counting to 8 for each of these. So I'm looking at this oxygen atom, and I'm saying 2, 4, 6, 8. I'm looking at the next oxygen atom. I'll do it in a different color, and I'm saying 2, 4, 6, 8. I'm looking at the last oxygen atom, and I'm saying 2, 4, 6, 8. Because this has got to get to octet for each of those atoms. Now here's the question. How do we know that the double bond is here and not here? We don't. Trick question. And what we used to think was that that double bond flipped back and forth. That was what chemists believed for a long time. That the electrons would pair here, and that the valence electrons would sort of split their time. Because remember, they're constantly moving. They're in a cloud. We can't even tell exactly where they really are. That they would split their time and go from here to there to here to there. And the way that it's shown then is what's called a resonance structure. And any time we have something with a double bond that could exist in more than one place, we have to show a resonance structure. And what we do with a resonance structure is we show a double-headed arrow in the middle, and we show both possibilities. We show a double-headed arrow in the middle, and we show both possibilities. Now what's interesting is what they now know is that in fact those electrons split the difference. So neither one is truly a single or a double bond. It's more like a bond and a half on each side. Electrons can do that. They can do all kinds of weird things. Because remember, these are representations of reality, not reality. There are no little dots floating around atomic symbols. That should give you enough background to start practicing the Lewis structures in your homework. And then next period I will print out an extra Lewis structures practice sheet with a key. You're going to need it. We're going to talk more about Lewis structures tomorrow and Thursday and Friday. You'll probably have a quiz Friday. So have a good day, folks.